Hello everyone. Hope everyone is feeling good today. Hope you can spare some time to watch this lecture later. Last week we talked about image segmentation, and we stopped about this slide, right? So we basically ended up at the second half of the lecture talking about the half transform and the Harris and the canny edge detection. Very important algorithms, two very traditional algorithms. Okay, so and then we stopped for a coffee and left the stuff for next week, which is today. So the idea in my schedule was to start with feature detection, but then when I looked at these at the notes for image segmentation, basically the best algorithms were left outside of last week's lecture. So this week, let's have a look at the second half of the chapter 10 on image segmentation, and we leave a feature detection for some future lecture. Okay, so this one is still very basic method, but very central to image segmentation, which we mentioned along the lectures, which is thresholding. Thresholding, one of the most obvious ways to segment background from foreground, or better to say, from segment foreground from background. So if you have, for instance, well-defined modes in your image histogram, the obvious way of segmenting, this could be background and this could be foreground, would just get this a threshold T. So whichever pixel has an intensity value that's less than this threshold will fall into this category. Whichever pixel that has a threshold that's greater than T will fall into this kind of mode. And we could work for various, we don't need only two, we may have three, more than three classes of pixels for segmentation. Thresholding becomes difficult. We'll see other or more important methods or more modern methods in this lecture. But let's start with thresholding, because there's one fundamental method in thresholding that's you can't leave a topic of talking about image segmentation without learning some of those. So if the threshold T depends on the position of the pixels, we basically say that this is a dynamic or adaptive thresholding. We're going to see in a few slides one adaptive thresholding method. But basically, what thresholding is that remember that in image, it's just a function of spatial coordinates that gives you an intensity value. So basically, if you're labeling foreground as 1 with a label 1 and background with a label 0, we are going to segment that by getting whatever intensity level is greater than a threshold, you label 1. If it's less than a threshold, you label 0. If you have more than 1, then you can have many labels, and you can basically, the labels, you decide what you're going to label your images, your segmented images. So some key factors for the success of thresholding, you probably have guessed that the separation between peaks is very important. Basically, the width and depth of the valley separating the histogram nodes is what dictates a good threshold separation. So this should be very well defined. If you have very well defined distributions of intensities, be it 2, 3, or n intensity distributions, that's a factor for the success of thresholding. And noise, always. When image processing, the real pain is handling noise. Because basically with noise, the modes are going to be broader. More noise, you just get broader and broader modes, and then they might occlude one another, so they might just merge with one another. The relative sizes of objects and background, obviously if you have a very large object as foreground and very little background, it's going to be difficult to segment. Illumination is a key factor, and uniformity of reflectance. Illumination and reflectance also are always interconnected, right? So, but let's see the issue of noise when you have threshold segmentation. So basically, this is a noiseless 8-bit image, just a synthetic image of some foreground picture, foreground object. It's this kind of Pac-Man object in a background that's this grayish background. Without any noise, this is pure gray, light gray. This is pure dark gray. So basically, will be just one peak here, counting the number of pixels that is, I think background is still larger, right? So it's dark gray, and another peak here with the light gray, right? If you have Gaussian additive noise, so we can still see a pretty well image, good image. We can still see pretty well this Pac-Man shaped image here. And the result of the histogram would be two shapes, two peaks, still fairly, let's say, segmentable by just simple thresholding, right? You just get the thresholding on 127, and you have you label this distribution with one label and this with another label. With a little more noise, right? So you have this image with a additive noise with meaning 0 standard deviation of 50 intensity levels, despite a lot of noise. But the human eye can still see the clear distinction, but then you can't threshold this anymore, right? So that's the effect of noise. It doesn't need to be a noise that affects the format of the picture, but it definitely affects your output of a thresholding segmentation procedure. There's no point here to segment foreground from background. Okay, yeah, in illumination. Still, the image, the center image with a little bit of noise, which more kind of a real image. It's a little bit of noise, but with uniform illumination. If the illumination is non-uniform, imagine that there is an intensity ramp here. So it's darker on this side and then goes to a lighter gray. And if you sum this image with that image, then we're going to get this result here. And the histogram is this. So that's a mess. That would it's just a little bit of difference in illumination. We don't see, well, we still see the peaks, but that's going to be very hard to actually find a very appropriate threshold here to segment into 3. Certainly, this is better because we have a larger valley here, but this will be very hard, right? The difference between this peak and this peak in the histogram would be pretty hard. Okay, so the basic thresholding method is the following, or it's called basic global thresholding method. So we're going to select an initial estimate for the global threshold. Just guess a number for segmenting foreground pixels and background pixels. Guess a number. Then you're going to use this threshold to segment the image using this, right? Equation 10.46. That's just that basic definition of thresholding. This will produce two groups of pixels, G1, which are all the pixels with intensity values that are greater than the threshold, and G2, which are all the pixels with intensity values that are less than the threshold. Then you get these two groups and compute the average mean intensities of each one of them. M1 for the group 1, M2 for the group 2. Then you compute a new threshold value. Basically, you get the midway between the mean 1 and mean 2, and set the new threshold values, and repeat these steps. Segment the image again, compute the average, get the mean. Segment the image, compute the average, and get the mean. So we're going to stop when the difference between the new threshold and the previous threshold is smaller than a predetermined value. So it's smaller than a certain error value here. This is the difference between the previous threshold and the current threshold. Okay, so that's semi-automatic, right? That's semi-automatic. Why is it semi-automatic? Because we still have to guess an initial threshold. Could be any guess, but still there is some human intervention in it. But the results are quite good. So get this fingerprint here. It's quite noisy, right? It's like this salt and pepper noise. This is the histogram of this image, and just by running this very simple, very simple algorithm for basic global thresholding, we're gonna get a much clearer segmented image, binary image now. With the backgrounds are all zero, are all white, and the foregrounds are all black. But can we do it better? And yes, of course you can. There is a great method, a very key algorithm. That's one of the algorithms that you cannot leave my image processing topic without at least seeing it in a couple of slides, which is the Ch10 method. Very famous, we used everywhere, especially in the industry. There's an implementation for it in OpenCV, and it's very simple to understand. It's very smart method. It's quite old also. I think it dates back from the 70s or something. I'm not sure. I have to look to be sure when it was. But it's quite old and quite successful. So what is the Ch10 method? It still looks at the histogram. Still looks at the intensity histogram. And then it automatically finds the global threshold by basically trying to maximize an equation, which this notion of a very central notion in statistics, that's the between class variance. Basic idea is then the individual classes should be distinct with respect to their pixels intensities, and the best threshold would, giving the best separation, would give the optimum between class variance. Basically, the between class variance is that the optimal, the maximum, is a point here where the difference between the variance here and the variance there is maximum, right? So that's the between class variance. So it's not so simple, right? So statistics is a very involving discipline, but it's not difficult at all. So it's all based on the Bayesian inferences, on applying the Bayesian rule. You can read that the book does a quite good job at developing these equations. I'm not going to develop in this lecture because otherwise it would take the entire lecture to do it step by step. But please have a look at pages 747 till 751. There's the whole derivation of the Ch10 method. So basically, this is the between class variance. It's basically a calculation where that involves the global mean. The global mean. So it means the mean value of every pixel intensities in the image that you want to segment, and the difference between the global mean times probability here that we're going to understand later, minus the cumulative mean computed for any k value. Why is this cumulative mean? So basically what it does, the global mean is a fixed value, right? The cumulative mean, you are going to take pixel by pixel. You're going to walk pixel by pixel, like you order your pixel intensity levels, and you get pixel by pixel calculating the cumulative values or the cumulative means of every time that you step forward on a pixel intensity. Maybe it will come clear in a demonstration that there is in the next slide. And this probability P1K It's just the probability of the intensity K falling on the component C1. And this is computed, oh, sorry, so component C1, computed for any K value. Then we get this maximum threshold, which is basically the maximum value of this of the between class variance. So that's the demonstration. So it's calculating this just red so red line here is the interclass variance. This is the distribution of the images. So basically, interclass variance is this is how this guy who generated that called the between class variance. It's the same concept. Let's see that again. So it passes by, and this what's doing is basically I can stop it. I can't stop it. So basically, at every step, it's calculating this bit. Every step, it is accumulating the mean value of intensity. So it's getting all the intensities up to that point, calculating the mean value, and calculating the with the mean value, you calculate the between class variance. So at every step, you basically what you have to do. This is fixed. At every step, you have to calculate that. That's just the accumulation of the intensity values as you are moving along the histogram. As you are moving along the histogram. And you also calculate this probability, which is nothing more than this, right? So you're just summing what? You're summing the number of points. Let's say this. Basically, the number of pixels from I0, from the zero intensity till the intensity K that you are walking through. I know this sounds a bit weird, but once you look into the derivations that developed by the book, this is just an output of the derivation using the Bayesian inferences within a maximization procedure in the Bayesian method. So basically, that Ch10 is very simple. So he walks through, goes accumulating this mean value, making this calculation here of the probability of the intensity K falling on component C1, and basically getting the maximum value of here. And as you see, the maximum value is where the derivative of the between class variance or the interclass variance is 0. Will be here, right? Will be here. And you see, when you finish the calculation, you get your threshold. Here comes the threshold. Hey, and then you segmented one side. You segmented these two portions of the images, either background and foreground. So this is the Ch10's algorithm in a nutshell. So you compute the normalized histogram of the input image, denote components of the histogram by Pi. So basically, what are the components? So every bin of the histogram is a component of the histogram, right? So compute the cumulative sums using equation 10.49, which is this, right? You're basically it's basically a cumulative sum of pixels intensities. Then you calculate the cumulative means. Then the computer call the global mean and get the between class variance term. And the Ch10 threshold K star is the value of K for which this between class variance is maximum. If the maximum is not unique, you can obtain a K star by averaging the values of the K corresponding maxima detected. Then you get the global variance using equation 10.58. That's this one, 10.58. It basically turns out to be this equation. So to find the K star, then, given that, we simply evaluate this equation for all integer values of K, given that the probability has to be between 0 and 1, and select the value of k that gives the maximum value for this equation here. Okay, so if you have some time, I think it's worth a look if you're interested in this kind of algorithms. It's a straightforward derivation. It will just take a lot of time to do it here, but basically this is the O2 method, right? Okay. And it gives you a quite good segmentation for a very simple method. So you see these are, I think these are some chemical property seen by a microscope, and you get a histogram of that. That's a mess. That's a mess. And what you see, there's no clear distinction here. It's very difficult to define. So if you use just a segmentation using the basic global threshold algorithms that we've seen at the very beginning of this lecture, we're going to get a segment that's like that. It's not a good segmentation. I want to get exactly these boundaries here. But by the O2 method, you get very clear segmentations, very clear segmentations. And I've used O2 segmentations in various robotics projects in the past. So it's a very powerful method still to use. And with noisy image, it's always a big trouble, right? There's always a big trouble. With noisy image, then when you get a histogram like that, O2, you can run O2 many times and you won't get anything. That's the best, the result of O2 methods trying to segment this, right? So it's not a proper segmentation. So whenever you have noise, whenever you have an image, the basic things, if you want to segment, the basic first step is to smooth it. Use a basic averaging kernel. In this example here, this image was smoothed using a 5x5 averaging kernel. So just by averaging it, then I have two nice distinctive histograms. By using O2, then I obtain in the end a quite clear segmented figure. But it's not perfect. O2 is not perfect. So if I want to segment this little point here on a noisy image, no matter how much I smooth it out, I still get a noisy segmentation. So why is that? Even this is without smoothing. That's the result of O2 segmentation without smoothing. This is the result of O2 segmentation after smoothing this image. So why is that? That's because the region that I need to segment, which is just this little cell here, this little point, is too small to contribute to the history. So O2 is based on its statistics. If you don't have enough statistics to make your inferences precise, then your method is just not the proper method to apply in this case. So they need to develop other methods. They need to either develop or get another method off the shelf. But O2 can also be extended to an arbitrary number of thresholds. We've seen in this image that O2 being applied for obtaining just one threshold, separating two modes of this histogram. But it can be extended to various thresholds in a very for instance, in this case, O2 has been applied to get three thresholds. This is then in an image of the iceberg. So our goal here is to segment the very white pixels, the light gray pixels, and the darker pixels. And this is the result of O2 extended for a number of thresholds. Another caveat of O2 is that as it's based on the statistics of the whole image. Remember that we're doing the statistics of the basic O2 method is doing statistics on the entire image. So if I have a non-uniform background, then like this, right? This is a typical noise called spot shading. Spot shading. I'm sure you've seen this kind of images many times before. That's basically a defect on your imaging systems. Usually, if you run O2 on this image, it's going to segment out important portions of your image, right? But we can do something different. So instead of doing the statistics, obtaining the statistics over the entire image, I can do the statistics over a window of the image. So I'll get a window of this image and run Otsu on just a small portion of it. Then I'll walk this window around and do Otsu here. So you see that of course this depends on how large is your corruption, is your corrupted image. That would depend on the size of your window, and also will impact on the efficiency of your algorithm. But again, as I said at the previous lecture, is that the main problem with the methods in computer vision and image processing is that you have to fiddle around with the parameters. People have been asking many questions in emails that, that's the algorithm that I'm developing is this, the algorithm that I'm developing is that. It's great they are developing algorithms, and you're basically getting annoyed, and for the right reasons, is that you need parameters. So you need to input parameters. In some way, you are it's doing a good job, but it still needs to set the right parameters. In this case, that's going to be the size of your window. But with the right window, you can get a pretty decent segmentation of this image here. So yeah, so the main notion is apply Otsu in blocks of the image, or in blocks of the image. So you just get portions of this image, or just do a moving window, as I explained in the previous slide. That's called the moving average method. And the moving average method is also good for sorting out this kind of sinusoidal shading. I'm sure you've seen this many times before. That's the effect of some how do you call noise in the electrical network. And basically, if you use the moving averages, you can segment this image in a quite clear way, much better than if you use the basic Otsu to segment this image. You get this very kind of patchy segmentation, right? So there are 2 people in the audience today. Congratulations, you've made it. Any questions so far? So that's great. So if you don't have any questions, we're going to move to a distinct kind of segmentation procedures. But just bear in mind that Otsu is a central method, and also this whole idea of thresholding an image. It doesn't have in this today so much applications in dynamic environments. Such as if you have an autonomous vehicle with distinct light conditions, distinct moving images. So you're not going to apply Otsu or thresholding on an autonomous vehicle. But if you are in an industrial setting with a controlled lighting, and you just want to develop a computer vision system that analyzes pieces in an assembly process, then Otsu is your preferred, your method of choice, right? Because it's simple, it's off the shelf, it's open source, and it's gonna work. So another way of segmenting the image is by region growing. Basically, what we want to get is to group pixels into larger regions based on some sort of criteria that we're going to call a predicate. So this usually starts with a set of seed points. Seed points in the regions that you want to segment. Again, parameters that you have to set up so that your system is gonna work. So from these seed points, you grow regions by appending to each seed similar neighboring pixels. So, for instance, you should get first define your criteria of similarity, depending on what you're segmenting your image on. So you may use color to segment images, so that you want. I'm looking at my wall here, and there's a portion of red patch in the wall, and a white surrounding, and a black object. If you want to segment in terms of color, you're gonna do your build your similarity criteria in terms of color, or I may be segmented in terms of texture. This will give a distinct region growing method, a distinct similarity criteria. And remember that texture is measured by the standard deviation, right, of pixels in a region. So get some similarity criteria, and the choice of similarity criteria depends on the problem in consideration, and obviously the type of image is also important. So that's the basic region growing algorithm. It's based on the idea of 8 connectivity. So we have this fxy denoting an input image, sxy denoting a seed array contains at the location of the seed points. Seed points is where I want to grow the regions, and zeros as well. And Q will denote the predicate. Q is the criteria that you're going to use to get pixels together. So basically, what pixels that are similar, that are closer to this criteria, will be grouped together. So what you're gonna do, you're gonna find all connected components in this seed array, and it reduces each connected component to 1 pixel. Remember connected components? We've seen this in the lecture about morphological operators. Right, so you're gonna form an image FQ such that at each point X and Y, you're gonna label each point with 1 if this pixel, you're going to label each pixel in this image if this pixel satisfies the predicate, the relative pixels, the pixel related to the original image. If it satisfies a given predicate, which is our similarity criteria. If it doesn't satisfy the predicate, it's going to be 0. Let G be an image formed by appending to each seed point S all the 1-value points of FQ. So all the points that agree that satisfy this predicate. And I'm going to form a new image. There are 8 connected to this seed point. Then we're just the final step to just label each connected component in this new image formed with the with all pixels that satisfy this predicate. And then we're going to label each region with a region label. It could be integers or letters or names and so on. So that's the segmented image with region growing. And that's quite powerful. Also, a very powerful, very direct method if you are in an industrial setting. So this is an example of an X-ray of a defective weld. Someone used a welding here, and you see that there are cracks in the weld. How do I know that they are cracks? Because light passes through cracks, right? The light does not pass through the metal. But if there are cracks, you're going to see pieces of light. And this is the histogram of that. So you see clearly that there are 3 pixels, but it would be difficult to use O2 to segment that. Maybe I could segment this background here with this middle point here, but not, or maybe this is the high intensity. So I could be able to segment this point here from the rest, but not, that won't be, as you see, the connection here is not very clear as the ones that we've seen when studying the O2 method. So the initial seed image is this one. And then the next stage is to transform the seeding image into single pixels. That is image D, right? final seed image points were enlarged for clarity, right? These are just points where I'm going to grow the regions from these points. It's the image E is just the absolute value of the difference between the seed value 255 and the original image. That's the histogram of E. And basically, if I used a global threshold with true thresholds to get this region, that's the result. To get this region segmented, to get the crack segmented, I get this segmentation. It's not very good, right? So it's not very good. It's not very clear what is what, and there is some confusion here between this portion of the image has been segmented with a distinct value from this other portion. So, and then this is the result by region growing. This is the result by region growing, right? So basically, from these points, then you just apply this. The predicate here will be similarity between intensity, because I just want to get the intensity, the highest intensities, pixels that are similar in terms of the highest intensities, and then grow, get the connected component algorithms that we've seen in the lecture about morphological operators, and that's the result of the segmentation procedure. Very clear, very clear. So region growing is very well applied. So this is just a summary of what I just explained. So determine the seed points. There's detection of features, so you know that cracks and porosities allow more X-ray to pass, so they're going to be bright spots. Find seed points by thresholding. Then specify the similarity criteria. Whichever satisfies the similarity, I'm going to label with 1. And with 0, the things that don't satisfy. Apply the similarity criteria, threshold the resulting image, and get only the regions containing the seeds. And I just forget about the other regions, right? That's very direct method, very, very powerful. Another important method is the region splitting and merging. So another important method in this context of region growing. So basically, the idea is to subdivide the image into a set of disjoint regions. Then what we're going to do, we're going to get from this initial segmentation, merge regions that are similar in terms of our similarity criteria. So basically, it's a modification of that. So I still have the similarity criteria, this predicate, but then instead of growing the region here, I'm going to just subdivide the image and merge regions that are similar, closer regions that are similar, and split regions that are different. So again, in a nutshell, that's given an image R in a predicate condition Q. First steps to subdivide the region successively into smaller and smaller quadrant regions, such that for any subquadrant, these predicates true. So for any subquadrant, for instance, if I'm segmenting with a color in terms of colors, any subquadrant will have the same color. Distinct subquadrants will have distinct colors, right? Start with the entire image region and go dividing it into quadrants. So if this is imagine that this slide is the image that I want to subdivide, I'll just get divided in the middle, in the horizontal, and in the middle, in the vertical, and get this would be one quadrant, another quadrant, another quadrant, and another quadrant. And then each one of these quadrants, I'm going to subdivide in quadrants. And then each one of these subquadrants, I'm going to divide in sub-subquadrants, and so on. So, and if the criteria is false for any quadrant, then you keep subdividing the quadrants into subquadrants, and this is always going to be stored in quad tree. A quad tree is just a data structure. It's a tree structure where it's a very nice data structure where you have at the root will be. This is applied to many fields, but in this particular algorithm, the root will be the entire image. Then the first children of the root will be the first quadrants. So here is the first children of root, quadrant 1, 2, 3, 4, and then and so on. So then these childrens of the childrens will be the quadrants within the quadrant. So for instance, if this region is still doesn't match the selection criteria, the similarity criteria, then I'll have to subdivide that into regions. And we stop when no further merging is possible. Okay, so that's one example of region splitting and merging. The idea is to segment the ring of this image of the Cygnus loop, and that's a cool example. I'll tell you why it's a cool example, because that's an example. So what's the characteristic of the ring? It's not color, right? It's texture. It's texture. So so basically what you do here, let's see, so this one segmentation by PartC, allowing the smallest quad region to be of the size of 32 by 32, and this will be of the size 16 by 16, of the size 8 by 8. So basically, you have a better definition if you allow for smaller regions in this PartC. There is always a caveat. The smaller the region you have for segmentation, the more memory you're going to use, and the longer it takes to process it all, right? And that's the cool stuff about this example. Which predicate have I used in order to grow? It's not region grow, to region split and merge this image. Is we're going to pick the region with the greatest standard deviation. So you see this standard deviation of this background will be 0. Homogeneous, right? The standard deviation is 0. There's basically no deviation from the mean value. The mean value is the value of everyone in the distribution. Whereas here, what's the standard deviation? Well, it's different from 0, but it's not great. And what about the ring? Oh, that's a great standard deviation. So you have a kind of well, it's more texturized, right? So the standard deviation is greater. Okay, so maybe this is a good point. I promised that I would give this lecture into small batches. I believe that this is a good point to do the first stop. Do you have any questions? If not, I'll just stop recording here and I'll start with one. This is this algorithm K-means was the reason why I didn't dump the second half of this chapter. K-means is the first machine learning algorithm that we're going to see in this course. And we're going to see K-means in a minute. So I'll just stop.